Today's topic is constraint geometric programming problem. As we have learned, the geometric programming problem involves the polynomials. Here also the constraint geometric programming problem we deal with the nonlinear programming problems where the objective function as well as the constraints involved are polynomial in nature. Let us consider the general constraint nonlinear the geometric programming problem in this way. Minimize. Now we consider the objective function as j is equal to 1 to n naught, as we have n naught number of terms in the objective function in the polynomial Cj and n number of decision variables are involved. That is why product of I is equal to 1 to n xi aij. This is a polynomial, as we know Cj's are positive and aij's are real numbers. Now, if this is so, then let me name this objective function as f naught x, where x is the decision variable tuple. Now, let us consider the constraint subject to, if there are p number of constraints are there of this form, we can consider the polynomial again here, and let us start the term from n naught plus 1. That is why n k minus 1 plus 1 to n k, where k is running from 1 to p number of constraints are involved, and we have Cj product of I is equal to 1 to n xi aij. Now, since this is a constraint, let us consider the constraint of the type less than, we can consider greater than equal to even. Now, this is a general geometric programming problem having constraints of the type less than equal to. Later I will discuss the model with greater than type inequation as well. Now, if this is so, then we can solve this problem with the method, extended method, as we have discussed about the unconstrained geometric programming problem. In the similar manner we can do it. As we did for the objective function, if you remember, we have used the Primal-dual relationship using arithmetic geometric mean inequality. The same thing let me extend for this method as well. How we could develop the Primal-dual relationship using the arithmetic geometric mean inequality, I am just now discuss. If we have the terms y1 to yn with the weights delta 1 to delta n, then we know the arithmetic mean is greater than equal to the geometric mean. Otherwise, mathematically we can say delta 1 y1, delta 2 y2, if we have say n number of terms delta n yn, if delta 1 delta 2 are the weights, let us divide with this. This corresponds to the arithmetic mean. This is always greater than equal to geometric mean. This is the power is delta 1 to delta n, and here we have y1 to the power delta 1, y2 to the power delta 2 in the similar way. And equality holds when these are all equal. Now, if this is so, then for the objective function where n naught terms are there, we can consider f is equal to, there are say n naught terms are there which are all individual monomials, then f is certainly is a polynomial, then u1, u2 up to un naught, if this is so, and let us consider delta j yj is equal to uj, all right. Then we can rewrite this arithmetic geometric mean inequality with the form and assume delta 1, delta 2 up to delta n naught is equal to 1. Then this arithmetic mean geometric mean inequality can be converted into u1 plus u2 up to un naught greater than equal to here delta j. There is a consideration as we did for the constraint geometric, the similar thing we will do here. This is equal to u1 by delta 1, y1 is equal to u1 by delta 1 to the power delta 1, u2 by delta 2 like this, un naught delta n naught. How we can consider delta naught, delta j is in such a way this holds. Let me do that part in the next. Let us consider delta j as uj divided by f star, where f star is the optimal solution of the objective function. Then we can say that at optimal point delta 1 would be u1 by f star, delta 2 is u2 by f star. In this way, if I just proceed further, then delta 2 by delta n naught is equal to 1, because summation of monomials at the optimal points divided by the objective functional value at the optimal point, which is same as the numerator. That is why this is coming is equal to 1. Now, from the previous, as we got that u1 plus u2, these are all, this is the objective function of the constraint geometric programming. This is greater than equal to u1 by delta 1, u2 by delta 2. From here we have developed the Primal-dual relationship. If we want to minimize this function in the primal, then we can have the dual is the maximization of this function, and with the further consideration orthogonality conditions and the normality condition. Now, how we can develop that? We know the orthogonality, as we know that uj's are equal to cj product of I is equal to 1 to n xi aij. That is why from here the right hand side part is equal to cj by delta j to the power delta j, and the product of all j's, j is equal to 1 to n naught, c1 by delta 1 to the power delta 1, c2 by delta 2 to the power delta 2, c n naught divided by delta n naught to the power delta n naught. In this way, this is the fact for us, and another term is there xi to the power product of xi's, I is equal to 1 to n number of decision variables are there, and this is equal to, this is summation of aij delta j, where j is again from 1 to n naught. Thus, we are maximizing this dual function instead of minimizing. That is the way we develop the methodology for dealing the geometric programming problem. Instead of the minimization of the primal, we converted it to the dual, and with that is the maximization of this objective function, and subject to the constraints that aij delta j is equal to 0, that is the orthogonality condition. And we have the normality condition, as we have developed summation of delta j is equal to 1. This is true for all I is equal to 1 to p, there I equal to 1 to n, where n number of decision variables are there, and j running from 1 to n naught, here also the same. That is the way we are considering the objective function. Now, what we got, thus we are getting here f k greater than equal to lambda k, and here we are having the product of y j delta j. What is yj? Just now we have considered that delta j yj is equal to fk, where j is running from nk minus 1 plus 1 to nk. Thus, if we consider these terms as uj's, the individual monomials, if we consider in this way, then this part can be written as lambda k. This is, we know uj is equal to uj summation of uj's, where uj equal to cj product of xi aij, and I is running from 1 to n, and for individual j we will get all the terms for the kth constraint left hand part, starting from j starts from nk minus 1 plus 1 to nk. Here also the same thing, we will get the cj delta j to the power delta j. There is a product of it, product of a j is equal to nk minus 1 plus 1 to nk. This is my yj delta j, and another set of terms are there. This is a product of xi's, and I is from 1 to n, and here we will get summation aij delta j, again the summation over j, alright. Now, let us take the power in the both side, as we got this should be lambda k, then only it works, otherwise it will not work. Let me freshly write it. 1, as we know that fk is less than equal to 1, with this consideration we can consider greater 1 greater than equal to fk to the power lambda k greater than equal to lambda k to the power lambda k, then the product j is equal to nk minus 1 plus 1 to nk cj by delta j to the power delta j, then product of n number of decision variables 1 to n xi summation over j, again j is from nk minus 1 plus 1 to nk aij delta j. This inequation we will get for all k's, where k is from 1 to p. That is why we will have p number of inequations. And if you remember from the objective function we got f naught greater than equal to, in the similar fashion there is another set j is equal to 1 to n naught cj by delta j to the power delta j, and product of I is equal to 1 to n xi aij delta j, j is equal to 1 to n naught. This sum, this j value depends on whether we are considering objective function or which constraint. If it is objective function, j will run from 1 to n naught. If we consider the first constraint, that is k is equal to 1, it will run from n naught plus 1 to n 1. If we consider the second constraint, it will run from n 1 plus 1 to n 2. In this way, we will have this set. Let me consider this is as A, and we have k number of b's. Then let us just multiply A and B k's together by considering k is equal to 1 to p. Then we will get a nice result in the next. We will get f naught in the right, because here we have 1 and here we have f naught. That is why if we multiply, it would be f naught and greater than equal to multiplication of all. If you see, we have a common term Cj by delta j to the power delta j. These all will get the product of it, which will run from 1 to np, all the terms together. And for this as well, we will get product of I is equal to 1 to n xi aij delta j, where j is equal to 1 to np, all the terms together. Thus, we can write f naught greater than equal to, and for all k we are getting lambda k to the power lambda k. That is why this is lambda k to the power lambda k, k is for p number of constraints, that is from 1 to p, and we will have Cj by delta j from the objective function as well as from the constraint. That is why if we consider all together, it will just vary from 1 to n p. That means we are considering all terms together, objective function as well as constraint, and there is another term I is equal to 1 to n x I summation a I j delta j. Here also we will have j from 1 to n p. Thus, we could see that again we could establish the primal dual relationship for the constraint geometric programming problem. We wanted to minimize this primal. Now we are getting the objective function of the dual which we need to maximize, and here also the decision variables are delta j's. Thus, we can write primal dual relationship in the next. And one thing I should mention here, that lambda k is equal to summation of delta j's, j is equal to n k minus 1 plus 1 to n k. We will use it in the next, this fact. And let us consider again summation a I j delta j is equal to 0, that is the orthogonality condition by considering j is equal to 1 to n p. And for the objective, from the objective function, as we have developed already delta summation of delta j, when j is from 1 to n naught, this is equal to 1. This is my orthogonality condition, and this is the normality condition. We will consider both the conditions together, and we can develop the primal dual relationship for the constraint optimization problem, and at the optimal level this functional value will be same. Primal objective functional value and the dual objective functional value will be same. Let me write down the primal dual relationship in specific in the next. What is the primal for the constraint optimization problem? Find x. Formally we can write in this way. Our objective is to find out the decision variable values which maximizes or minimizes. I am considering the minimization problem. Minimizes f naught, this is equal to summation j is equal to 1 to n naught c j. These are all the monomials. As a whole, this is a polynomial for us. J is equal to 1 to, I am sorry, this is I is equal to 1 to n number of variables are there. Subject to, let me consider f1x less than equal to 1, f2x less than equal to 1. In this way there are p number of constraints, fpx less than is equal to 1, where f1x is equal to j is running from n naught plus 1 to n1, as I repeatedly said before. Cj in the same pattern, let me write it down, I is equal to 1 to n xi a I j, alright. And f2. Similarly, if I consider, let me consider this as fk, this is again k minus 1 to k etc. K is from 1 to p. This is the primal I considered at the initial level, and my concern is to find out the dual, because we will not deal with the primal problem, we will deal with the dual problem. That is why if I write down the dual of this primal, that would be maximization of product of lambda k to the power lambda k, k is from 1 to p. We will have product of Cj by delta j's to the power delta j, j is from 1 to np, alright. And subject to, we have the normality condition zj is delta j is equal to 1 for all the terms in the objective function. We have the orthogonality condition aij delta j is equal to 0, j is from 1 to np again for all i's, and here we have considered lambda k equal to summation of delta j's. For individual constraints we will have summation of delta j's. Thus, j is equal to nk minus 1 plus 1 to nk. This is my lambda k. And what is the objective? Objective is to find delta j's. Thus, how many delta j's we are having? We have delta j's delta 1, delta 2, delta n naught from the objective function. From the first constraint we have delta n naught plus 1 to delta n 1. From the second we have delta n 1 plus 1 to delta n 2. In this way the last one we will get delta n p, and this is the decision, these are the decision variables for this dual of this geometric programming problem, and we have to consider the constraint as all delta j's are greater than or equal to 0. That is the consideration. Whatever we got for a constraint geometric programming, we will solve the dual. Let us construct the dual like this for a numerical example. Here also the same fact is there, here is one fact is there, that is called the degree of difficulty. Degree of difficulty is very important for geometric programming problem. Generally the degree of difficulty we consider for the constraint geometric programming problem as total number of terms means total number of monomials, total number of terms in the polynomials involved in the objective function as well as constraint. How many terms we have? We have np number of terms in the problem minus number of decision variables, that is n minus 1. This is the degree of difficulty for the constraint geometric programming problem. If the degree of difficulty is 0, then we will get the unique solution. If the degree of difficulty is not 0, we will get the alternative multiple solution. Let us apply this one for a problem, for an example minimization of f naught x. This is the monomial 40 divided by x1, x2, x3. Take another monomial 40 x2, x3 subject to x1, x3 by 2 plus x1, x4 by, there are 4 2, x1, x2 divided by 4 less than equal to 1. There are 3 variables, decision variables x1, x2 and x3. Let us consider these are all equal to 1. We have to construct the dual objective function first. For the dual objective function there are 2 terms are involved. One is the Cj by delta j to the power delta j. How many delta j's will be here? That depends on how many terms are involved in the problem. Here how many terms we have? 1, 2, 3, 4, 4 terms are there. That is why we have 4 deltas in this problem. Thus, we will have C1 by delta 1 to the power delta 1, C2 by delta 2 to the power delta 2. This is coming from the objective function because objective function has 2 terms. From the constraint we have another 2 terms C3 and C4, that is 1 by 2 and 1 by 4. C3 divided by delta 3 to the power delta 3, C4 to the power delta 4 to the power delta 4. This is the set. What about this set? This set is the lambda k, where lambda k is the summation of delta j's. We are considering those delta j's which are involved in the constraints, and for the objective function the corresponding delta j's we are considering in the normality condition. This is the normality condition. That is why we will put as a constraint here, but the lambda k, this we will consider in the objective function. Thus, the new problem we have to formulate, that is the dual of the given primal problem, where we will have the objective function in this fashion and we will have the normality condition and we will have the orthogonality condition. First let us find out what is the degree of difficulty for this problem. Here the degree of difficulty equal to total number of terms are 4, number of decision variables 3 minus 1. Thus, the degree of difficulty equal to 0. That's we can conclude that we will get the unique solution for this geometric programming problem. Now, if we consider the dual, then dual objective function, let me construct the dual objective function first. Maximization of C1 by delta 1, that is my 40, C1 is 40 by delta 1 to the power delta 1. Here also 40 by delta 2, here 1 by 2, 1 by 2 delta 3, here it is 1 by 4, delta 4, delta 4. What about lambda k? We are having only 2, delta 3 and delta 4, we are having only 1 lambda. Thus, lambda k to the power lambda k. Thus, delta 3, delta 4, that is my lambda k here, lambda 1, only one constraint we have to the power delta 3 plus delta 4. This is the dual objective function, and what are the constraints we have? We have the normality condition, that is delta 1 plus delta 2 plus delta 3 is equal to 1. That is, these deltas are coming from the objective function. No, delta 3 is not there, delta 1 plus delta 2 equal to 1, this is the only constraint. And another constraint we have summation aij delta j. How we will get aij summation? Let us form the matrix, 3 variables are there, that is why let us see the power of x1 in each term. Power of x1 here is 1, power of x1 here is 0, here it is 1, here it is 1. Similarly, for x2 power is, this is minus 1, for x2 the power is minus 1, 0, no, second is 1, 0, 1. Similarly, for x3 minus 1, 1, 1 and 0, and we have aij delta j, that is why delta 2, delta 3, delta 4 equal to 0. This is the orthogonality condition for us. Now, we need to solve this problem. Here this can be solved and we will get the unique solution for this. In the next, if we just solve it, then we will get the values for delta 1 is equal to 2 by 3, delta 2 equal to 1 by 3, delta 3 equal to 1 by 3 and delta 4 equal to 1 by 4, and corresponding dual objective functional value at optimal point, if I consider as a star, this is equal to, we are getting 60. This is same as f naught x star, that is the optimal value of the objective function of the primal problem. And by considering this value as we did for the unconstrained geometric programming problem, in the similar fashion we can get the value for x1 as equal to 2, x2 equal to 1 and x3 equal to half. Thus, problem is solved. Now, this is the simplest problem, we got the unique solution. Let us take another problem where we will get the multiple solution, where the degree of difficulty is more than 0, that is 1. We are considering the problem f0x equal to 40, x1 to the power minus 1, x2 to the power minus half, x3 minus 1, 20 x1 x3, 20 x1 x2 x3, subject to f1x equal to 1 by 3, x1 minus 2, x2 minus 2 plus 4 by 3, x2 to the power half, x3 to the power minus 1 less than equal to 1. And this is the problem for us. 3 variables are involved, and let us consider the degree of difficulty for this problem. How many terms are here? 1, 2, 3, 4, 5, 5 terms are here, and number of decision variables are 3. That is why NP minus total number of variables minus 1. this is coming 1, that is the degree of difficulty is 1, we will get the unique solution. We need to pass the value for one variable and we will get the set of another variable. Now, for this problem we can construct the dual. How to construct the dual? Dual is the maximization problem, maximization of C1 delta 1, that is why it is coming 40 by delta 1 to the power delta 1, 20 by delta 2, delta 2, these are the terms we are getting from the objective function delta 3, and from the constraint we are getting delta 4 and 4 by 3 delta 5 to the power delta 5, and there is one constraint, that is why we have the lambda k to the power lambda k, that is only for the constraint, that is delta 4 plus delta 5 to the power delta 4 plus delta 5, that is all. And what about the constraint set? First of all, the normality condition that is coming from the objective function, 4 deltas are involved for that, this is equal to 1, and summation of delta I j we will get from here again the set. And how many deltas? Delta 1, delta 2, delta 3, delta 4, delta 5. For the first variable x1, we are having minus 1, 1, 1, minus 2, 0. For x2, minus half, 0, 1, minus 2, half. For x3, minus 1, 1, 1, 0, minus 1. This is equal to 0. These are the orthogonality conditions. Since we have degree of difficulty equal to 1, we need to pass the value, and if I just write down the equations, we will have equations here, and if we just pass a value of for a delta here, because our problem is to find out the values of delta which maximizes this dual objective function. If we consider delta 2 is equal to r, then we will see that we will get delta 1 is equal to 1 minus 2 r. This is simple calculation we can do from the constraint set. Delta 3 equal to r and delta 4 equal to minus half plus 2 r and delta 5 equal to minus 1 plus 4 r. Alright. Once we are doing so, by passing the value, if we just pass a value for r here, we will get a set of deltas, and we could see that from this constraint, we could see that since deltas are all positive, we can have the limit for r as 1 by 4 and half, because delta 4 is greater than 0, delta 5 is also greater than 0, greater than equal to 0. That means delta 4 is minus half plus 2 r greater than equal to 0, and here we are getting 1 plus 4 r greater than equal to 0. Another condition, we can have 1 minus 2 r greater than equal to 0, that is my delta 1. From this condition we can develop the limit for r. Thus, our problem has been reduced to a problem of single variable maximization of, in place of delta 1 we will put these values, delta 1 equal to 1 minus 2 r etc. If I just put it here, then we will get 40 divided by 1 minus 2 r to the power 1 minus 2 r, 20 by r to the power 2 r, 2 by 3 into 4 r minus 1 to the power delta 3, that is 4 r minus 1 by 2, 4 by 3 into 4 r minus 1, 4 r minus 1, that is delta 4. Then we have 3 4 r minus 1 divided by 2, 3 4 r minus 1 by 2, subject to r is half. And from here, this is a problem of single variable r. we can get the value for r star equal to 0.4. Once we get the value 0.4, the dual objective function at the optimal level would be 99.9999, and from here we will get the values. Once r is fixed, we can get the value for delta 1, we can get the value for delta 2, delta 3, delta 4, delta 5, all the values. And once we know the dual objective functional optimal value, this is the optimal value for the primal as well. Thus, considering that fact, as we know for the geometric programming problem, first we are finding out the objective functional value at the optimal level. If we are satisfied with if our requirement is satisfied, then we can stop our processing there, otherwise we can go for the optimal value of the decision variables as well at the next, by considering the relationship we have developed before, and from there we can get x1 equal to 1, x2 equal to 1 and x3 equal to 2. This is the optimal solution for the primal geometric programming problem. Now, this is the problem we have developed, where we have considered the problem, the constraints are of the type less than equal to. Now, if we have the constraint of general type, then how we can solve the problem? Let me discuss that part in the next. Thus, we have the problem minimization of f0x subject to few fk's are less than equal to 1 and few fk's are greater than equal to 1. If this is the case, then how to handle this problem? We can consider, say, k is from, we have considered k is from n naught plus 1 n naught plus 1 to say some value n m, and here it is starting from n m plus 1 to n p. That means few constraints are of the type less than equal to and few constraints are of the type greater than equal to. Then how to handle this problem? Let me discuss. We can use the signum function here. We can join both the types together by using the signum function sigma k, where we are considering 1 minus f k, and this is greater than equal to 0. We can consider, if we consider as z k equal to this, then sigma k is equal to plus 1 if f k x is less than equal to 1, and this is minus 1 if f k x is greater than 1. Clear? And with this signum function, we can write down this set of constraints as g k greater than equal to 0. This can be written very easily. Now, here also the same thing, this is the primal problem for us. We can go for the dual of it, and dual objective dual form I am just writing down in the next of this prime for the same primal. Maximize k is equal to 1 to p lambda k to the power signum k lambda k, because these lambda k's are coming from the set of constraints, and sigma k signum function is involved. Sigma k is equal to 1 if it is of less than type, and it is equal to minus 1 if it is of greater than equal to type. That is why we have to write lambda k to the power sigma k lambda k, and there are the terms z is equal to 1 to n p c j by delta j. Here also the same for the constraint set, but delta signum function will not be there, that would be 1 only for the objective function, and we have the constraint subject to j is equal to 1 to n naught delta j equal to 1, that is the normality condition coming from the set of deltas obtained from the objective function, and from the constraint as we have taken a I j delta j. Here we will consider signum function sigma j j is from 1 to np equal to 0, I equal to 1 to n. Here also the degree of difficulty would be total number of terms of the total number of polynomial terms minus number of decision variables minus 1. Let us consider one example with this fact, where both the greater than type and the less than type are involved together. We are considering the function f x1, x2, x3 minus 1, delta 4, subject to two constraints we have, one is of less than type, another is of greater than type, 3x1, x3 minus 1, x4 2 plus 4, x3 minus 1, x4 minus 1 greater than equal to 1, and another constraint 5 x1 x2 less than equal to 1. Here also if we see the degree of difficulty, that would be the total number of terms 1, 2, 3, 4, 5, 6, number of decision variables 4 and minus 1. That is why degree of difficulty is 1 here. Thus, we will not get the unique solution, but we can formulate the dual of this primal. Let me write down the objective function here, maximization, and we have first the Cj by delta j to the power delta j. We have what? Cj is 1 by delta 1 to the power delta 1, 2 by delta 2 to the power delta 2, 10 by delta 3 to the power delta 3. These are three things are coming from the coefficients of the objective functions. Now, from the constraint we have three by delta 4 to the power minus delta 4, because here the constraint is of the type greater than equal to, thus we are getting minus sign here, 4 by delta 5 to the power minus delta 5, and for the next constraint we have the less than type, that is why the signum function is 1. We have 5 by delta 6 to the power delta 6, signum function is 1 here, and we have 6 deltas because total number of terms are 6, and there will be another term from the constraint set, one set from these two and another set is from here. One set means delta 1, delta 2, delta 3, here we are getting only delta 4 plus delta 5. This is to the power minus delta 4 plus delta 5, because the signum function value is minus 1, and we have another one that is from here, that is delta 6 to the power delta 6. Clear? This is one lambda k, this is another lambda k. Here only one term is there in the next constraint, that is why only delta 6 is coming here. Thus, this is the objective function for this problem. Now, if I just construct the constraint set for this, that would be equal to, from the objective function the normality condition we are getting delta 1 plus delta 2 plus delta 3 is equal to 1, and here also the same, we will have the Aijxj, here delta 1, delta 2, delta 3, delta 4, delta 5, delta 6, this equal to 0. Now, let us construct the value x11 minus 1, 1. From the next, as we see, we have the greater than type constraint, that is why we have to consider the negative of the power. As we see in this constraint x1 power is 1, but here the constraint is greater than equal to, that is why we need to consider as minus 1, because signum function will be multiplied here. Thus, it is minus 1, 0, 1. for x 2, 2 minus 3 0 0 0 1. For x 3 this is minus 1 0 1 minus 1. You see here the power of x 3 is minus 1, but since the constraint is of type greater than equal to, we will not take minus 1, we will consider plus 1 here. Thus, this is 1 1 0, and for the fourth decision variable powers are 0 1 0, and here we are getting minus 2 1 and 0. Thus, these are the set of constraints. This is the normality condition and this is the orthogonality condition. If I write down in detail, then we will get the set as, write down in a different color, delta 3 equal to 1, and here we are getting delta 1 minus delta 2 plus delta 3 minus delta 4 plus delta 6 equal to 0. From the second, 2 delta 1 minus 3 delta 2 plus delta 6 equal to 0. From the third, minus delta 1 plus delta 3 plus delta 4 plus delta 5 equal to 0. From the next, delta 1 0, that is why this is delta 2 only starts with that, delta 2, delta 3, delta 4 plus delta 5 equal to 0. And these are the now you see we have how many equations we are having? We are having 1, 2, 3, 4, 5 and number of variables 6, and as we have already calculated the degree of difficulty 1, that is why we need to pass the value for one variable and we will get the solution for this. Let me write down the solution, just do the calculations accordingly. And we will get the value for deltas in this way. From here we will get delta 2 is equal to 8 delta 1 minus 4, delta 3 equal to minus 9 delta 1 plus 5, delta 4 equal to 6 delta 1 minus 3, delta 5 equal to 4 delta 1 minus 2, delta 6 equal to 22 delta 1 minus 12. Thus, we are giving the value for delta 1 and we will get the values for delta 2. Thus, we will get infinite number of solutions here. Solution is not unique. Here also the same thing. In the objective function, we will write down the delta 2 to delta 6 in terms of deltas, then we will have the maximization of this as a function of single variable. We can use the classical optimization technique for solving it and we will get the optimal solution for this problem. Thus, in this way we could develop the methodology for solving the general constraint geometric programming problem, where we have the mixed type of constraints, mixed type of inequality constraint, where the constraints are of the type greater than type or the less than type. Both the types I have developed and I have shown you the example for it. And that is all for about the constraint geometric programming problem. Thank you very much.